Good morning, everyone. It's my pleasure to have a chance to give this lecture about electromagnetics, simulation principles and methods. I'm working for EDR Meditech company, which is Nordic. We have offices in more or less all Nordic countries and UK. My background is more or less electronics manufacturing, EMC, antenna, RF, clean room, something like that. And during the last 3.5 years, I have been working for this company with the focus on high frequency simulations. On top of that, of course, low frequency is kind of one part of the simulations we are combining with the high frequency and so on. So shortly, the company, we are about 130 people. We have the headquarters in Oslo. I'm based in Tampere office. We have about 20 people in Finland, a bit more people in Norway and Sweden, and then we have something like 10 people in the UK. We have a lot of customers in Nordic area. Simulations are widely used by the industry. Of course, this includes not only electronics, but also mechanics, fluent, thermal, low frequency, high frequency, and so on. So more or less all the physics. Yeah, we have something mostly diploma engineers and doctors working for that. So heavily engineering related team. And we are also doing the cooperation with the Nordic universities as a part of the contract with the main software supplier, Ansys Corporation from USA. So basically, we are channel partner for the Ansys platform. Today, I am mostly focusing, of course, to Ansys platform, but I will also explain shortly what other tools, what other principles there exist for the electromagnetics simulations. So on top of that we are a channel partner, we do also services to industry, keep trainings, and this university cooperation is one part of the job what we are doing. So basically, this is the split for today. I'm starting to speak about why somebody is doing electromagnetic simulations. Then what kind of simulations can be done, what we typically try to avoid. Then I will go through different tools and principles used in simulations and what kind of software packages there is and what are the main, what's the main purpose of each. Then some example simulations. And this is slightly different today that, I'm mostly focusing on the slides today. We have the second session on Friday, which is now going to be more like a live demos with the software. So how to do the simulations. And at the university, for all the students, you have actually access on these software packages from Ansys webpage. So there's a student version, which is something you can download. And there's also a chance to use the software at the university computer classes if there's an Ansys electronics package installed or other Ansys products. But basically for the Friday, it's not the idea that you are using the software. You can use it, of course, if you want to, but basically I'm just going through different software packages, showing the functionality, what you can do with the software. And today we are focusing more or less on principles and methods. So basically, if we are thinking about this simulation, area, we can kind of rigidly split it in three. We are speaking about mechanics, fluids, and electromagnetics. And it's not so that we are just kind of doing a single physics. We can also send data. The simulation tools can share data or even have dynamic links between. So we are many times nowadays doing multi-physics, so that we are coupling. For example, if you have a high power electronics, like power electronics, it will heat something, and then you can have structural changes, warping, expansion, shrinking, and basically that will change once again RF frequency, for example. On the other side, we need to cool down electronics. One of the main design limitations nowadays with electronics is the heat. And for that, we need to control airflow, liquid cooling, and that's where the fluid dynamics comes really heavily on top of the electromagnetics. So we are able to do different kind of simulations for same kind of applications or this systems or products based on the same based on the same CAD data. We can use the same CAD data for electromagnetics fluid as we are using for mechanical simulations. And there's a huge number of different solvers, principles, mathematics you can do simulations. This is just giving you a small snapshot of mechanical simulations, and where you can apply something like that. The same for the fluid. We have the engine, combustion engine, like how the gasoline will burn inside of the motor. Then we have a cooling. We have the rotor design, acoustics design, and of course we have the airflow, friction, aerodynamics, and then we have complex scenarios where the environment will affect the helicopter airstream, for example, when you are landing to the closed small area, plus the wind, of course, and so on. For electromagnetics, we can use the same CAD once again. Okay, if I'm saying the same CAD, it's, I mean, the body, of course, then if the more you go to details, then you have to kind of have more detailed CAD data for example, for the electronics here. Antenna arrays, you can analyze where to place the antenna. Actually, most of these tools are based on space and military, and that has been more or less the driving force to do simulations for electromagnetics already since 1960, 1970. And a single helicopter, for example, or fighter or something, can have something like 15 antennas active at the same time. And the idea is that all the antennas can work without coupling to each other too much. So you have really extremely sensitive passive antennas and beside of that, you can have hundreds of watts or kilowatts power radio communication antennas. So we have a huge scale with the radio signal electromagnetic waves on top of the helicopter surface and close to the helicopter. So that's one huge area. Lightning strikes has been one of the must simulations already since, I don't know exactly, maybe 1960, 1970, when the computation power came strong enough to do it. And that's one of the few electromagnetic simulations which is required for commercial systems. Otherwise, you can do more or less do everything with measurements based on the qualification. But simulating or measuring something like a lightning strike is really, really expensive and difficult, and you need hardware for that. You can do it with simulation. So this is done for all of the airplanes, spacecrafts, and so on. Then we have movements with system, like a car has the wheels spinning. With the helicopter, we had the blades rotating. It will change the radio wave you are receiving and sending. So we have plenty of different level of scaling with electromagnetic simulations, starting from antenna arrays, EMC, ESD, lightning strike, radio communication, coupling, interference. Then we have all kind of component level amplifiers, circuit simulations, and so on. So this is typically such a wide area that people will focus only on some specific area. And on this picture, we don't have actually the DC power grid simulations, but that's a second huge area, how to optimize power components, power electronics, switches, relays, and how to minimize losses in a grid system, and so on. So so this slide, basically, you're thinking now different electromagnetic simulations. Typically, we can think about electromagnetic simulation with any platform from Ansys or other suppliers. We can split it kind of 4 main groups. In this case, the HFSS is the high frequency simulation solutions. SI-Wave is a platform or software you can do circuit board simulations. So you are analyzing multi-layer circuit boards with which can have a few up to maybe 20 layers and tens of thousands of components and so on. Then we have the ISPAC, which is the cooling. So the cooling is the number 3. Any electronics you design more or less needs to consider heat somehow. Maybe only area the heat is not a main challenge is passive RFID antenna components or something where you have extremely low power levels. But even that, you have the temperature and the frequency dependency existing. So if you have extremely hot surface, your antenna tuning can be switching to the side. So you have to think about the temperature all the time with electronics. And the Maxwell here is the DC power electronics. So Maxwell means it's basically all these are using, except, okay, the ISPAC is different physics, but HFSS, SI-Wave, and Maxwell, they are all using basically the Maxwell equations. You should be somehow familiar for the mathematics, but we are just slightly using different principles in each, really, to make it more accurate. For low frequency in this case means a DC, or let's say just tens of hertz frequency or something like that. So basically there's 4: high frequency, circuit boards, cooling, and DC electronics. The SI-Wave and HFSS, these are actually both kind of doing high frequency and low frequency, a bit same way as the Maxwell, but Maxwell is specialized on that. On top of that, SI-Wave is only doing circuit board, whereas the HFSS here is a full 3D, which is kind of full 3D CAD you bring in. SI-Wave is taking circuit board layout data for that, and it's optimized for that. And there's specific reasons for this split, and I will go through the details later on. Okay, this is just once again a little bit more details of this split. So HFSS is a high frequency. And you can do the circuit, you can do even circuit board simulations with the HFSS, but the main challenge that if you try to do full circuit board simulations with full 3D, it's too heavy for computers. You have to simplify something, and that's why we have a specific tools for circuit boards. In low frequency range, we can think about that we need to use different techniques, physics, when we are analyzing, for example, electric motors. Nowadays, this electric motors is a heavy area for simulations because of electrification of vehicles, cars, even the heavy industry systems are starting to use electric motors more and more. So efficiency is the number one. And then it comes the heat, and which is solved typically with ice pack. Of course, you can do some of these simulations in 2D, just taking a kind of a cut plane and doing simulations. But as you can see, the electric motor here, it has 3-dimensional shape. And you have to think about how these electromagnetic waves, or magnetic waves, mostly in this case, are bending in different areas of the motor in order to optimize that. And these are extremely heavy simulations. You need lots of computing power, and you have to have high detail model of the motor, or the windings and where the magnets are. And typically those materials are also non-linear, which is making that quite challenging. There's one more software mentioned here, Q3D. I will shortly explain that later on. It's basically you can simplify complex 3D structures to RLC circuit models, typically used with power electronics, with IGBT, power distribution, and converters, and typically found in nowadays actually in all electric motors and windmills and something like that. So why? So I was saying that really few simulations are required from the industry. So if you go to qualification test the standards or documents, you can see that more or less everything can be or should be done by using measurements. So if you are willing to qualify your mobile phone charger, you have to measure that it's not giving any electric shocks, so the safety is ensured. And you have to measure that it's not giving too much conductive noise to the grid, or you are not getting too much radiation, electromagnetic radiation out of the charger when it's functional. So basically, there's nobody requesting you to do the simulation, but there's really good reasons why industry is heavily depending nowadays on simulations. And the number one is speed. For example, mobile phones. If you design a mobile phone, every prototype takes something like 3 to 4 months to get a functional prototype, and you don't really you can't really speed it up because you have to manufacture all the components and the tools to make those components for each prototype, and it's really expensive. So mobile phone industry, for example, they typically have only 2 prototypes, and the third one is the sales product. And a mobile phone is a really complex system, and the only way that they can do it is to use full simulation model out of that. So you are designing, for example, mobile phones purely based on small approved component sub-circuits and simulations. So they combine these 2. So it's speeding up the R&D. That's the key. So that's how they get money back from simulations. And part of that is the validation of the design before you do any hardware prototype. So basically, you know that the system is running before you get the prototype. You still need hardware prototypes, and there's some hiccups with simulations. And one typical challenge is any non-linearity with the operation. So if you are not having linear systems, you are creating surprises. And that's something you can see more or less only with measurements. Optimizing and testing different design variations. That's something you really want to use simulations for. Changing something with the prototype, hardware prototype, takes typically hours or even weeks in the worst case, to do, even months in heavy system. But with simulations, you can typically do variations in tens of minutes or hours or something like that. So you can use that for optimize the system. Then we have some specific areas where we are willing to use simulations to predict, for example, the lifetime. A good example is heating with specific components. So you might have, or you will have, some specific components which are heating up. And anytime the system heats up and cools down, you will have some stress for all the solder joints or component structures inside of the component. And it will break because of mechanics during the time. So we can use simulations to give a lifetime estimation for electric components or systems. And it's all heavily related to cooling and mechanics. So you are typically using multi-physics simulations here. And when you have a challenge, you can use simulations to find and fix design problems. It's based on variation. So you can try that. If I have now EMC challenge with this frequency, so if I add this 5 or 10 picofarad capacitor in this place or this place, can I fix it? This is easy to do with simulations. Sometimes really challenging to do with hardware. Then we are using simulations a lot for visualizing problems and for sales. It's quite surprising, but engineers are salespeople. Many times we have to sell the idea. This design is better. This is really good. We can use hard technical jargon and numbers to explain that, yeah, this antenna is 2 dB better than the other antenna. This is why we should use it. But sometimes when you discuss with customers, which are not really understanding what you're speaking about, just make a picture with red and blue colors. Red is bad, blue is good, and it's easy to understand. So like the small demo up right corner, this is actually DC electrostatics. So if you have a high voltage component coming down like a relay or conductor, how the E field in this case is distributed around the surface and where the sparking might occur and in what state. So basically you can visualize what happens when something is moving, when something's touching and sending radio signal or something like that. So you can get nice pictures. So it's a sales support. So related to R&D speed and costs, EMC is one specific area. It's part of the qualification of electronic systems or components even. So you have to do that with measurements. And basically you have to go to a specific lab with specific tools to do something qualification. And typically system is already done. It's ready, or it's at least a prototype when you do this. You can't do that without hardware. So it can be really expensive to do these tests. And sometimes these labs are occupied most of the time. So you have to reserve the time 2 months ahead. So one way is to limit the need of hard testing is really just copy paste the EMC lab and do the same in simulation and try to predict as many problems as possible with simulations. And then it's only the top of the measurement qualification is just to verify the results and fix, hopefully, minor problems which are not visible with simulations. So anyway, there's plenty of, so when we're speaking about electromagnetic simulations, we are not speaking a single product. We are speaking about a family of different tools, different software packages. And the traditional challenge for that is that each of these tools has had different user interface, different way of using. And industry is now more or less moving heavily to use platform simulation systems. And from Ansys' point of view, this is the Ansys electronic desktop, which means basically that you have a single user interface for most of the software packages. So you don't have to learn to use different user interface, where to open the files, how to bring the CAD data inside. It all works the same way. But the mathematics and we call solvers. Solvers are the mathematic tools you are using to do the calculations. Those are something you kind of bring in and do different physics. You can do low frequency physics, high frequency physics, circuit board simulations, cooling simulations with the same user interface. So nowadays the version actually is 2020 R2, but basically the software packages are still the same, visible here. So, by the way, if thinking about what other software packages are widely used, is Ansys is the leading. I think so. The Ansys is 5 times bigger than the next 5 simulation suppliers, if we look in the global market. The other suppliers, major suppliers, especially in Nordic area, they are more or less COMSOL multiphysics, commonly used by universities, less used by the industry. Then there's the Dassault for electronics. They have the microwave studio. For high frequency, they have the CSD. That's pretty commonly used, specific in Europe, less in, based on my understanding, less in Asia and USA. But commonly used by, used to be commonly used by, for example, Nokia Corporation. It's an Ericsson, for example, if thinking about now Finland and Sweden. I used to use the CSD before this Ansys. Then we have some smaller EM Pro is for the high frequency one software package. And then we have plenty of small software packages which are able to do some specific area quite well. So absolutely, there's no only Ansys, there's plenty of different software packages. Still the same principles mostly are with all this, because the mathematics is basically the same. So the mathematics is the common language. It's the user interface and the details, how you use that. That's something which depends quite a lot of the software you are using. So if thinking about different applications, where you can do the simulations and what kind of tools you are using, basically we can do with this high frequency package really simple and really complex designs. Especially in Sweden, you have like at Chalmers University, they are doing terahertz design. So they are on the right side. They are tiny components, complex components, and small. So really high frequency, small devices, really demanding simulations. On the left corner, we have a single circuit board with maybe Bluetooth or Wi-Fi. Bluetooth and Wi-Fi are nowadays, let's say, really basics. So if you are designing Bluetooth or Wi-Fi radio systems, there's nothing specific anymore. Those are commonly used. Commonly, people have common skills to design and optimize those tools. So I would say that that's not rocket science anymore. More or less, you can also buy those components really well, which are really well designed. The only job is to make the integration of Bluetooth module into your system and so on. So it's more integration. Less people are designing Bluetooth and Wi-Fi modules and antenna systems by themselves. They typically buy the component, and that's it. It's so efficient nowadays. So basically, you can do simple things, complex things with the same software package. And then if you go to larger scale, bigger designs like airplanes, cars or something, you slightly need to change the math you are using. In the lower row here, we are using the full 3D electromagnetic simulations. This layer, you can see this kind of HFS IE and FEBI. I will explain more, a little bit more of that, but we are doing simplifications with the CAD in order to be able to handle bigger systems. The problem is that these are 3D environment simulations. And in 3D, if the size increases and the frequency increases, you can think about how many small details you have to include on your simulation. And it gets heavy to do the computing. Then if you go even bigger systems, once again, you might need to change the math. You can still maybe use the same software, but you are using different solver. So the different solvers are using different mathematics. And in the shooting and bouncing rates, you can think about that as a laser beam or LIDAR principle. You are shooting electromagnetic wave radar lines to all directions. And then you are calculating how the electromagnetic waves behave. So we are not actually modeling the whole 3D space, the volume anymore. We are just approximating that we have air, we can have vacuum in space, or we have seawater under the sea. So you are just approximating the media between the antenna source and the target. And then you can combine this. So you can really combine really high detail, small array antenna and an airplane and do the simulation on that. Once again, now you are not actually switching the physics to different or the solvers, but you are bringing this high detail solution like this component here on top of your airplane. And you are modeling the airplane with different solver like this FEBI, which is expecting that the surface is carbon fiber or aluminium, for example. So it's conductive. If it's conductive, we can simplify the math and see how the electromagnetic currents, surface charges are spreading on top of the airplane. And if we have a second antenna here on tail, we can see that how much this antenna is coupling to that antenna by just following the surface currents and of course the radiative signal, if that's a key coupling principle. So basically, yes, we can do a lot, but we have to know how to do it. We have to combine different mathematics solvers and maybe use them in parallel on top of the same design. So this is the magic we can do nowadays with simulations. We don't have really limitations anymore because we have so huge numbers of different solvers. So once again, short kind of summary. We have the HFSS with the shooting bouncing ray feature. This is the full 3D heavy simulation. principle, the most accurate way to do it can do also circuit boards if the circuit board is small. Then we have the SOA, which is able to do really heavy circuit board simulations. It's using different math, simplifying something. We have the Q3D, get RLC, resistor, inductance, capacitor models out of complex 3D structures. SPICE, always, we always use SPICE simulations, circuit simulations. So try to do all the simulations as simple as possible, and that's where we use SPICE. And then we have specialized EMA 3D, which is a cable, EMC, and coupling noise simulations. Cables are a huge headache to industry. If you go to electric car, you have the high voltage charging cable. On top of that, you have all the wires controlling ECUs, electronic control units. Everything works with electronics, electricity, and you have lots of high noise components in your car. And you need to pass all the qualification tests and safety tests. So we need to simulate how the cables are behaving from electromagnetics point of view. And we can call kind of supporting software is the ISPAC, which is the coding of that. Maybe I know that in Sweden you're doing close operation with Ericsson, for example, and if you go to, I was just looking the Black Friday offers, and we can see that the 5G and mobile phones are kind of now the hot case for the Christmas season, and 5G mobile phones are having totally different antenna design compared to 4G and 3G antennas. The 5G typically has multiple antennas, and many times the antennas are metric antennas. So they need absolutely different simulation measurement systems. You can't even measure metric antennas anymore. It's based on software. Antenna signal is made by using software and phase shift. So the antennas are metric antennas, and that's purely designed based on simulations. So basically, we always have a software package, and then we have add-on options on top of that. So we have the core, and then you will typically buy, or it's integrated to the software, different sub functions we can call. So we have the core software, and on top of that we have toolkits kind of. So for example, you can do eye diagram simulations. You can do optimization with Optimetrics or some kind of tool which is kind of designed to make variations easy way, efficient way, do design of experiments or something like that. Then you can have RF tools, especially like microwave designs. Then you most likely need to go to cloud computing with distributed simulation. So you are splitting the design in small pieces and sending it to, let's say, 200 cores or GPUs to do the calculation, and so on. So every software you are using for simulations has nowadays add-on toolkits, which are bringing extra features, giving more functionality, making the software more user-friendly to use. So if looking what type of simulations industry do, we more or less always start from SPICE, circuit simple 1D or 1.5D or 2D, how people think this about. It's based on a simple RLC analysis. So just conductive waves, electromagnetic waves, no radiation, no coupling, nothing. This is ideal. And you can do quite a lot with a SPICE. So basically the SPICE circuit also comes with any this kind of free, if you buy or you have access on 3D simulation software packages, it will always include SPICE. And there's a main reason for that. And that's the little rectangular box here. This is actually a parameter file. And this parameter file is explaining frequency dependent, maybe nonlinear behavior of some specific component in your system. But the power supplies and the load, they can many times be simplified with resistors, capacitors, inductors. And of course, you can have transmission lines, you can have switches, any active components. You can bring even IBIS, IBIS, small signal behavior models inside, and so on. So we always start with the SPICE. And these components you can see here can be replaced with more complex models, which can be, for example, S parameter files or impedance files, which are explaining more complex behavior. So for example, this S parameter file can come from level 2. This is the circuit board simulation. So for example, you have a high speed DDR memory clock trace or net inside of your circuit board. And you need to explain how it behaves with higher frequencies, where you absolutely have coupling the high frequency behavior, and you can't really use any more SPICE model to explain how this trace is behaving. So you have to simulate and get mathematical representation or simplification of that trace. You can simulate it then in 2D. Somebody people say this is 2.5D. This is the circuit board layout design where you have multi-layer system, VRs, and all kind of impedance changes, coupling, cross-talk behavior. But you can actually export the data from here and bring it to the SPICE. And we can also say that we can do this in full 3D. So 3D means that we are also calculating electromagnetic waves around the circuit board. In 2D, we are just calculating the electromagnetic waves inside and on top of the circuit board. If we do that in the 3D, we draw a bigger box around this circuit board and do the math also in air or space, whatever you have on top of the up and down and side of the circuit board. And we can include even the cables and 3D components and everything like that. And you can also kind of extrapolate data you can bring into the SPICE. Once again, you can do SPICE simulations. So this is the most common way industry will do. They focus on SPICE and they do 2D, 3D simulations to explain the coupling or the 3D behavior, nonlinear behavior in SPICE. If that's not possible, then we do the code simulations. We are able to simulate the circuit board, and maybe if this is the array antenna, we are simulating that maybe in 3D or 2D, and then we bring it on top of the helicopter here and place the array antenna here, and then we simulate multiple physics at the same time. We are sending the data from the antenna, and it will couple to the surface of the helicopter, and it will change the way the radiation pattern or the amplification of the signal, the gain, in different directions, and then we can see it in system level how it behaves. And this is typically something we are doing in EMC lab, for example, for the complex system. This is something the circuit designer is doing, and this is what the circuit board designer is doing, and this is what typically the type approval guys need to think about more, at least. So thinking about different simulations, typically they focus on, let's look into the industry, what they do the most with simulations. Everything was more or less starting up from antennas. So a simple monopole antenna, you can do with basic analytic equations, and you will get more or less accurate results. But as soon as you bring several antennas together, close each other, or you bring different surface materials close to the antennas, it will change the behavior of the antenna, and it gets really complex. As soon as you go to array antennas, it gets so complex that you need software to do the simulation on top of the 3D behavior description of the antenna. So they are using simulations to optimize antennas. They're looking how strong signal you will get from antenna to antenna. Or if you are an EMC guy, you look how much the antenna is giving noise to my sensitive signal traces on the circuit board, or to the other antenna, or how much emissions you will get, or how well it survives the immunity tests, and so on. Then we have the huge second area is the EMC. Sub area is the electrostatic discharge. EMC is the that the system is kind of fulfilling requirements set by the standardization or the functionality requirements. So immunity and emissions. It's a big challenge with digital electronics nowadays, because you just create a lot of noise, electromagnetic noise, and you need to handle that, suppress or prevent or filter or whatever you are doing, the principles. So a lot of EMC design is about groundings, how to do the groundings for your system. But there's a lot of filtering and high frequencies measurements you need to do for qualification. And that's where we can use simulations to help with. And then actually the next, from my point of view, I can see that the heat is the next. A lot of simulations are done. Where is the heat coming out? How much I can cool it down? How hot it will get? And by that way, we can predict the lifetime. And then comes a lot of different reasons, like what kind of component parameter I should choose. For example, you can choose capacitor value based on simulations, simple thing, but you have to sweep the capacitance value and run the simulation multiple times. Safe operation. This typically is related to high voltage or power electronics. And in power electronics, we have the optimization challenge. As the less power kind of lost, the more efficient system, the more efficient the system will be, the cheaper it will be to use. And now, by the way, the EU regulation is forcing the electric motors, for example, to be, what was the latest number? Was it 97, 98% efficient? Now I speak out the big electric motors for pumps and sewage pumps and clean water pumps and something. So there's a really heavy requirements, and it's impossible to do those motors anymore by doing measurements. You have to do simulations to optimize the design. In high frequency RF design, you are doing a lot of simulations, especially for eye diagrams, timing, filtering, balancing, and so on. So this huge area of different simulations you have to do. But this is so wide area that nobody is able to do all kind of simulations or electromagnetic designs anymore. You have to focus on some specific areas. So if you go to industry, you can find antenna guys, you can find EMC guys, you can find power electronics guys, heat, the cooling heat guys. So they are doing their own area and they try to communicate with each other. And it helps a lot that you are using the same simulation platform so that you can sift simulation results from guy to guy so that they can use the data from different simulations to optimize the system level operation. So I said we do a lot of nice pictures, and this is really efficient to sell the idea, or explain the problem and sell the idea how to fix it, or sell your product. My product is this good. You can see this from this picture, how well it radiates, or how well it survives external noise, and so on. And it's some issues are easy to explain with pictures. Like here, you have a simple circuit board antenna, BIFA antenna, maybe, or something like that. If you have the circuit board alone, nothing around, this is the radiation pattern. The red means that there's a good radio signal that direction. As soon as you plug it into your printer with plastics, metal frame, and those will change the antenna behavior or the radiation pattern and the gain. And this is the end result. So in this green and blue area, you don't really get any radio signal coming through. Or so if you are using mobile phone or Wi-Fi network or something to place this printer into web, you have to rotate the printer in order to get the signal maybe to your router or something. So this is a common challenge with antenna guys. So it works perfectly when you design it alone, but as soon as you integrate something into a system, you will change the signal. And this is also a reason for EMC problems. So the system integration will destroy your EMC performance, and you will get lots of noise issues, coupling issues, noise in your data, and so on. If you go to work for base stations or military area, you are going to work nowadays with high frequency in these metric antennas. So this is kind of typical military radar, how it behaves, how it works. Actually, the 5G is a bit similar, not much more simple, of course, in mobile phones, but the base stations, they have this kind of antenna elements with a lot of small antennas. You are switching on and off based on where you are willing to send the data, which direction you are willing to send the data. And that's actually software controlled system, but you have to design the hardware for that. And engineers, we like numbers, pictures, where we can see the value. So this is typically what we are looking for. 2D graphs, radiation pattern, gain, S parameters. S parameter is in high frequency, it's the de facto stimulation outcome, or impedance, or the in time domain, we are looking for reflections and bouncing of signals and so on. We can also do kind of what if analysis, like in here, we have slot gap in a metal plate, and how much signal you will get, through the slot, and the signal is coming from the right side, and the left side is the leakage. So it's really easy to do visualizations and measure. So we can measure any point in this design with simulations, which is really hard with measurements. In the future, I can see that simulations are more or less the #1 design tool for electronics. It's shifting heavily on that way. So you will start with simulations and you end up with kind of measurements. You are just verifying that the results are correct. And with based on the measurements, you will do maybe small minor improvements in the design, and that's it. So, and it's going to be more automated, more user-friendly, more toolkits are actually helping with that. And you will get more and more accurate source data for your simulations. You are going to do more multiphysics in general. Of course, some specific designers, they focus just for eye diagram, and that's the top what they do. But many other people, they need to do and combine different solvers, different solutions together. Why more simulations? Also that the frequencies are going up. So we are now moving in higher and higher frequencies because the speed, data speed, and because there's more free frequency bands. So we are already occupied more or less every usable low, let's say from below 2.5 gigahertz, we are already using all the frequency bands existing. Not always efficient way. So we are changing those, some frequency bands are kind of let free for different applications. But if you are looking for new solutions for the radio systems, you have to go to higher frequencies. And if you want to have speed, you are going to use high frequency in your circuit board. So that's why all the memory processors, everything, they are using higher and higher frequencies. Of course, there's limits coming up, and one of that is the power consumption. So we try to use as low frequency as feasible, but that's kind of moving up all the time. So that means it's really hard to predict what happens. Just simple mathematics. We have to do simulations for that. Car industry is driving force nowadays for electronics. It's surprising, but it used to be telecommunication, but car industry is now, based on the messages we will get, using more. I think so. It's close to the same level of using simulations than electronics, telecommunication industry. It's basically because everything works with electricity, and this battery electric power motor is just superior over consumption engine, gasoline engines, diesel engines. So that's where they are going. Security. Okay, security. The other word is military. Military applications are heavily depending on. So in every conflict, the first victim is information. So we are twisting information, giving false information, or blocking information. So any conflict you can see, the first thing you will see is that something happens with radio waves. They are sending lots of noise. They are blocking GPS. They are blocking radio channels, TV channels, mobile phones channels, radar channels. Absolutely. So security from immunity and kind of also to cause some trouble both ways. That's a huge area where we can use electromagnetics. Frequencies. You can see applications up to 250 gigahertz, and there's some specific components. We are speaking terahertz nowadays. Yeah, so basically at this point, I would like to have a break. Any proposal how much we should have? 10 minutes, is it okay?
Yeah, it's okay. Yeah.
Okay, let's continue after 10 minutes.
Yep.
Thank you.
Sure.